Hey, thanks everyone for coming. I'm going to be talking about our research into trying to make bare metal or monolithic firmware fuzzing better in paper MultiFuzz, multi-stream fuzzer for testing monolithic firmware. So the first thing I wanted to talk about is exactly what type of firmware we're looking at, and that's the one where it performs kind of direct hardware accesses without any kind of easily harnessable hardware abstraction layer and no operating system in between. And these type of firmware exist in a fairly wide range of devices, such as 3D printers, CNC machines, and various other embedded systems. And fuzzing is, really effective at finding bugs in a lot of different software, but there's some challenges in applying that to firmware. And kind of the key challenge for this type of firmware is actually feeding it the inputs. So this firmware makes a lot of direct interactions with very varied and potentially complex hardware, and these interactions occur through memory mapped I/O typically. So therefore, in order to effectively test this, we need the fuzzer to provide inputs for each of the hardware accesses that it performs. And one approach that has been taken to fuzzing these things is to reuse the type of file-based input generation from a traditional fuzzer such as AFL and kind of map the inputs it generates byte by byte to every MMI access that the firmware performs. However, when you do this retrofitting of this file-based input format, it introduces a lot of inefficiencies in the input which don't properly map to what the hardware actually does with the input, which makes the fuzzer less able to generate inputs that effectively fuzz the firmware. And so for our research, we focused on kind of three key problems in these type of file-based fuzzing things that cause it to behave less well for firmware fuzzing. So the first thing is input stability, which essentially is about how a small change to the input can have a drastic influence over how the input is eventually consumed by the fuzzer. And then ineffective input generation, we find that the file-based fuzzers tend to get stuck at points where it's just waiting for more data. And then data scattering, which causes related data to be put in various different places in the input generation processes, which prevent certain mutation strategies from working effectively. So for the first problem, it's kind of the most immediate one you'll encounter, and I have a simple code example here. So for the first time we have a certain hardware access, we read the first byte of the input, which happens to be a 0, which doesn't match the condition. So we skip that, the if body, and move on to the next if statement and consume the next byte there. However, if a mutation occurs and adjusts that, so now that bit is set, we take a different path through the firmware, which means the byte which was consumed by a different peripheral later is now consumed by this different place, and so we don't make that condition, the later condition, anymore. So this makes it so it's harder for the feedback mechanisms that fuzzers traditionally use to effectively explore deeper into the program because mutations can tend to break things. However, if we switch to a different representation where each of the different peripherals are assigned a different section of the input, any mutations we can make sure that the input bytes are still consumed by the exact same peripheral each time. So the next problem I'm going to talk about is related to the fact that firmware typically operates in a very event-driven manner. And this causes that there to be locations in the code where the firmware just wants a sufficient amount of data for it to make pass to the more interesting things that we care about fuzzing. So in this case, I have a low-level example where we just want to read a correct value from a certain peripheral register indicating that the serial device is synchronized. And then a high-level example which wants to print a potentially very large string to a serial port, which might involve a very complex interaction of multiple peripheral reads and writes, including a synchronization step. In order for the fuzzer to make it through that print statement, if the string is long, it's going to have to generate quite a lot of input values that match all the relative constraints that indicate that the firmware has consumed the input string from the serial device. So we address this by using the fact that the multi-stream input representation makes it easier to know what values to actually extend the input sequence by to make progress through this faster. So here's 3 different extension strategies we use. The first one is simply to just extend it with random value, which works a surprisingly large amount of the time, because quite often there's no specific value that the firmware is looking for. If it's something like an accelerometer value or a temperature reading, all we want is just some value produced in order to make progress. The next thing that comes up quite often is the same interaction with that hardware is done multiple times repeatedly. So from that synchronization example before, it might request that the peripheral is synchronized many, many times in the firmware, and you always want the same value. The same value always satisfies that request. So by copying previous values earlier in the stream, which we know are likely to be related to the same thing because they're associated with the same hardware peripheral register, it can allow us to make progress a lot quicker through those. And finally, in certain cases, we're looking for very specific values in order to have some sort of complex conditions. We use a combination of a per-stream dictionary, which I'm not going to go into too much depth in the talk, but you can check out the paper for further details, and a couple of predefined, well-known, interesting edge cases for the firmware, such as all ones or all zeros, which tend to actually work very well at satisfying many of the checks that get performed. And all of these stages are done adaptively when the fuzzer detects that it's ran it to the end of one of these streams, and multiple of them can be stacked together if multiple extensions are required in order to progress past a certain point. And the final problem I'm going to talk about is data scattering. So here we might have a function that interacts or parses some data from a buffer, but as it turns out in the actual firmware code to fill that buffer, there's a bunch of interspersed other accesses in between the actual data we care about. With a file-based input representation, this ends up meaning the bytes we want to investigate are so far apart in the input that it's hard to do effective mutations to find them. But with a multi-stream input representation, these tend to get squashed back down into a single contiguous block. It makes certain mutations much easier to apply to those operations. So one example of that is a pretty well-known mutation approach used in traditional fuzzing, which is this idea of logging and finding comparisons in the program and replacing the operands. And that works basically out of the box with a multi-stream input representation. We take our input, we run it through the program with some instrumentation to collect comparisons, and then search through each stream independently for a copy of the data we're interested in, perform a replacement step, allowing us to satisfy a bunch of different comparison operations. So we can combine all of these features together to build a new monolithic firmware fuzzer, which takes advantage of this multi-stream input representation with the various different length extension stages and stream-specific mutation techniques to better fuzz firmware and hopefully find more bugs. There's a bunch of other smaller details in the paper if you're interested in, so please check that out or talk to me afterwards. So we evaluated this on a bunch of different firmware targets, and compared to file-based fuzzing, firmware fuzzers achieves better or equivalent coverage on all of them and can find all bugs as well as some new bugs. And I thought interesting case study, I took one of the bugs and added some steps to the fuzzer so it could basically list the chain of mutations it performed in order to find this particular bug, and it kind of demonstrates how all the features work together in order to find it. So for this particular bug, we have a command which takes a key value pair, and if we have a specifically bad key in there, it stores some invalid value in memory, and when we run the command again, it tries to print out that value and crashes the firmware. So the first step is it needs to generate enough data to make it through these different serial operations, including printing the serial port and reading from the serial port. And this basically happens instantly as it rapidly extends the inputs with the right values. Next, it needs to find the right command. And so this is found with that input to state replacement step, and can directly paste that into the input at the correct location and execute that command. Then we see the other length extension strategy where we copy previous values, and this includes both copying the data and copying the ready event, indicating that the data has been received from the fuzzer, allowing us to have the two commands ready there. And then the final step is regular traditional mutational fuzzing techniques where we end up with this corrupted URI parameter. And this is essentially the MultiFuzz. It's multi-stream input representation in order to better fuzz monolithic firmware and outperforms file-based fuzzings in both code coverage and bug detection. And it's fully open source on GitHub, and feel free to ask questions or contact me via email.